Imagine you're describing the motion of a car on a busy highway. You might say it's traveling at 60 miles per hour, which gives us an idea of its speed. This tells us the speed, but not the direction in which the car is moving. To fully describe the car's motion, we need a concept that captures both magnitude, which is speed, and direction, like north or south. This is where vectors come in, providing a complete picture. A vector is a mathematical entity that has both magnitude and direction, making it very useful in physics and engineering. Think of it as an arrow pointing in a specific direction. The length of the arrow represents the magnitude, and the direction the arrow points in represents, well, the direction of the vector. This makes vectors perfect for representing quantities like velocity, force, and displacement, which all have a direction associated with them, unlike simple numbers. Vectors are different from scalars, which only have magnitude and no direction. Temperature, mass, and time are examples of scalars, as they do not involve direction. Scalars are represented by a single number, making them simpler but less informative in some contexts. Vectors, on the other hand, need both a number for magnitude and a direction to be fully described, providing a richer set of information. Mathematically, we represent vectors using different notations. One common way is to use bold lowercase letters, like A or V. Another way is to use an arrow above the letter, like a with an arrow or V with an arrow. When we draw vectors, we use arrows. The tail of the arrow represents the starting point, and the head of the arrow represents the ending point. The direction the arrow points in is the direction of the vector. The length of the arrow is proportional to the magnitude of the vector. We can also represent vectors using coordinates. In a two-dimensional space, we use two coordinates, x and y, to specify a vector's location. In three-dimensional space, we use three coordinates, x, y, and z. These coordinates tell us how far the vector extends in each direction. Just like numbers, vectors come in different types. Let's explore three important ones: zero vectors, unit vectors, and position vectors. A zero vector, denoted by 0 with an arrow, has 0 magnitude and no specific direction. It's like an arrow with no length. Think of it as representing no movement or no force. A unit vector is a vector with a magnitude of 1. They are often used to indicate direction. We can obtain a unit vector from any non-zero vector by dividing the vector by its magnitude. A position vector, also called a location vector, is used to describe the position of a point in space relative to a fixed reference point called the origin. The tail of the position vector is at the origin, and the head is at the point's location. Just like we can add and subtract numbers, we can also add and subtract vectors. Vector addition combines two or more vectors to find their combined effect. Think of it like this. If you walk 3 meters east and then 4 meters north, your total displacement is not 7 meters. It's the vector sum of the two individual displacements. To add vectors graphically, we place the tail of the second vector at the head of the first vector. The vector that connects the tail of the first vector to the head of the second vector represents the sum, also known as the resultant vector. Vector subtraction is similar. To subtract vector b from vector a, we add the negative of b to a. The negative of a vector has the same magnitude but points in the opposite direction. Section 5. Scalar multiplication of vectors. So, we can multiply a vector by a scalar, which is just a regular number. This operation scales the vector's magnitude without changing its direction, unless the scalar is negative, in which case the direction is reversed. For instance, multiplying a vector by 2 doubles its length, while multiplying it by 1/2 halves its length. Multiplying by -1 reverses the direction of the vector, but keeps the magnitude the same. Scalar multiplication is useful in many situations. For example, in physics, we multiply the mass of an object by its acceleration, which is a vector, to find the force, also a vector, acting on it. Section 6. Vector properties, making operations easier. In this section, we will explore how understanding these properties can simplify complex mathematical operations. Just like addition and multiplication of numbers have properties like commutativity and associativity, vector operations also have certain properties. These properties are fundamental in making vector calculations more intuitive and manageable. These properties make it easier to work with vectors and simplify calculations. By understanding these properties, we can solve vector problems more efficiently and accurately. The commutative property of vector addition tells us that the order in which we add vectors doesn't matter. This means that whether we add vector A to vector B or vector B to vector A, the result will be the same. So, A plus B is the same as B plus A. The associative property of vector addition states that when adding 3 or more vectors, the grouping doesn't matter. This property is particularly useful when dealing with multiple vectors. So, A plus B plus C is the same as A plus B plus C. The distributive property connects scalar multiplication with vector addition. This property allows us to distribute a scalar across a sum of vectors. It states that a scalar multiplied by the sum of 2 vectors is the same as the sum of the scalar multiplied by each vector individually. This is a key concept in vector algebra. So, Ka plus B equals Ka plus Kb, where K is a scalar. These properties are not just mathematical curiosities, they are essential tools that help us understand and manipulate vectors in various fields. They reflect the way vectors behave in the real world, making them powerful tools for modeling physical phenomena. From engineering to physics, these properties enable us to solve real-world problems with greater ease and precision. Section 7. Vectors in physics. Vectors are essential in physics. They help us understand and describe motion, forces, fields, and many other physical quantities. For example, velocity is a vector quantity. It tells us not only how fast an object is moving, but also in what direction. Similarly, acceleration, which is the rate of change of velocity, is also a vector. Forces are also represented by vectors. They have both magnitude and direction. When multiple forces act on an object, we use vector addition to find the net force, which determines the object's acceleration. Vectors are also used to represent electric and magnetic fields, which are regions where electric charges or magnets experience forces. Section 8. Vectors in engineering. Vectors are just as crucial in engineering as they are in physics. They provide a way to represent quantities that have both magnitude and direction. Engineers use vectors to design bridges, buildings, airplanes, and countless other structures and systems. These vectors help in visualizing and calculating forces and movements. For example, when designing a bridge, engineers need to calculate the forces acting on different parts of the structure. This ensures the bridge can withstand various loads and stresses. These forces, represented by vectors, arise from the weight of the bridge itself, the traffic it carries, and environmental factors like wind. Each of these factors must be carefully analyzed. In aerospace engineering, vectors are used to describe the motion of aircraft and spacecraft. They help in understanding the dynamics of flight. Velocity, acceleration, lift, drag, thrust. All these quantities are vectors, and understanding them is essential for designing safe and efficient flying machines. Proper vector analysis ensures optimal performance. Vectors are also used in computer graphics, robotics, and many other engineering disciplines. They help in creating realistic simulations and precise movements. Their ability to represent both magnitude and direction makes them indispensable tools for solving real-world engineering problems. Engineers rely on vectors to innovate and improve technology. Section 9. Conclusion: Vectors in our world. Vectors might seem like abstract mathematical concepts, but they are deeply intertwined with our physical world. From the motion of planets to the forces holding buildings together, vectors are everywhere. Understanding vectors allows us to describe and analyze the world around us with greater precision and depth. They are essential tools for scientists, engineers, and anyone interested in understanding how things work. As you delve deeper into physics, engineering, or any other scientific discipline, you'll find that vectors are your constant companions, helping you unravel the complexities of the universe.